to a session key that is used for encrypting bulk data. Whenever a user joins or leaves the group, you need to update this session key to ensure security. And if the group is large, you have your key management problem because now you must update this session key in an efficient and scalable manner. So a lot of schemes have been proposed to solve this problem, and we broadly classify them into two categories. First is logical key hierarchies that use a trusted group controller. Here the group controller maintains a tree of all the long-term symmetric keys and efficiently updates the session key on change. Basically, it pushes it out. The drawback is that the group controller is completely trusted. So if an adversary compromises the group controller, it gets access to all the long-term keys as well as session key of all the groups that the group controller supports. On the other kind of schemes are more decentralized or contributor key agreement schemes, which are perhaps more elegant in nature and do not involve a group controller. And they update the session keys amongst the users using distributed protocols. Unfortunately, they do not scale as well and also impose a slightly higher overhead on the individual group members. So what we have done is use the proxy encryption idea to try to get the best of both worlds to some extent. Our scheme is called TASK, which is a tree-based group key management scheme with asymmetric split keys. The scheme is as efficient and as scalable as LKH, essentially order log n. Furthermore, we have a partially trusted group controller. That is, the group controller does not store encryption keys. Instead, it only stores proxy keys to do the transformation. So even if the group controller is compromised, the confidentiality of the messages is not lost. Therefore, the group controller is no longer a single point of security failure. Furthermore, recovery is much simpler because you have not lost any long-term security secrets. The assumption for our protocol is that all messages are signed, and this is a common assumption by most group key management protocol. Another problem is that the group controller and a member are not simultaneously compromised, and I'll talk about this assumption a little later. To get an idea of how our keys work, here are the key trees for both LKH as well as TASK. So on the left is LKH. As we can see, these are all symmetric keys. On the top half are the keys that are stored in the group controller, and bottom half are the keys that are stored by the member. Each member has a set of keys, specifically order log n, from its position in the leaf node all the way to the root. The group controller uses the long-term keys as well as intermediate node keys to update the session key for each member. And the session key is nothing but the root key here. For our scheme TASK, these are all asymmetric keys, in particular Elgamal keys. And the keys are not common to members and group controllers, but they do have a relationship. For a common index, the private keys at the member and the corresponding private keys of the proxy keys at the group controller add up to the same value called GKEK, the group key encrypting key. The session key is a hash of the root private key stored by the members. Since the group controller does not store the session key or the long-term member keys, its trust liability is minimized. But the fact that it has these proxy keys allows it to do the transformation in an efficient manner. So let's see how the proxy stuff works for member leave event. So we have a group of 9 members, and member 9 decides to leave. It sends a message to the group controller, or it lost network connectivity and it needs to be kicked out. Now we have to update the session key for every member. The group controller identifies a sponsor, say member M8. The member generates a random number and adds it to its set of existing keys to update them. It then encrypts this random number with its own public key, G to the KM8, and sends it to the group controller. The group controller now uses proxy transformation to convert this into minimum set of messages needed to send R, the random number R, out to all the other members. In this case, it will be order log n messages. So to send a message to members 1, 2, and 3, you can use the proxy key K123. To send it to 4, 5, 6, use this key, and send it to member 7, use its private key. The members now decrypt R and add it to their own set of private keys. Now all the members compute the hash of the new root private key, and that's the new session key. The group controller also adds a random number to its set of private keys, and the alt set of keys are updated, a new session key has been established, and member 9 has been excluded. So I won't go into details of the join protocol. It's a lot simpler because like LKH, you can use the current session key to send the random value R. Members can decrypt this value with their existing session key, and the sponsor sends a set of keys to the joining user who obviously does not have any keys to begin with. And furthermore, the joining member also contributes a share to its private key, and the system is updated. We've done a complexity analysis of these two schemes, and it turns out that our scheme is as scalable as LKH. We have an additional communication round. This is needed for sending the messages to the joining user. And we have some exponentiation that do not exist in LKH because LKH is a symmetric key-based scheme, while ours is public key-based scheme. However, the exponentiations are either a constant number or exponential. We are currently implementing a prototype of the system, and we've got about 9,000 or so lines of code written and partially tested. Initial results are promising, but we haven't completed this testing. So looking at this, we've also identified a couple of challenges for proxy encryption, and we're working to address them. First is the need to generate a proxy key without a trusted third party. So if you remember in the initial example we gave, we had a proxy key, which is the difference between the decryption keys of you, Alice, and Bob. How is that difference generated? If you have a trusted server that's computing the difference, then that trusted server becomes a point of liability. So you need a way to do it in a distributed manner. So Atenlese et al. At Johns Hopkins has developed a solution that addresses this with a novel identity-based encryption scheme. That's done in the context of delegation rights, so it needs a notion of a resource owner, which is not applicable to all scenarios. For example, in group communication, there is no resource owner. Furthermore, it also requires the users to manage 2 private keys instead of 1, so that's a higher overhead. What we have done is to solve this problem using distributed key generation process by sending an additional round of messages with this random number addition and subtraction. My intuition is there is a better scheme out there than both of these to address this challenge. The second problem is resilience to collusion. As I mentioned in our scheme, both in the cells as well as in the group key management scheme, if you add the proxy values and a member's value, you get the group key. And that can be used by the adversary to violate the confidentiality of the system. So this is actually a consequence of using proxy encryption. So you could view it as a limitation of proxy encryption or a challenge to be addressed. And we're exploring solutions that address this problem. We have some initial results, but we still have to work on this a little more. So in conclusion, we show that confidentiality is needed to secure messaging infrastructures. Solutions today either provide no support for this or use trusted servers. Consequently, those servers bear significant trust liabilities. We propose the use of proxy encryption techniques to solve this problem and produce novel solutions that minimize the trust liabilities in servers supporting confidentiality. We've looked at 3 infrastructures, so let's spend a couple of minutes to see what are the different properties of these systems. So first beginning with email. So in an email system, the latencies are very reasonable. If people are okay to wait a second or even a few minutes before the emails are delivered. The group membership is known because once you have a set of valid list subscribers, you know the group. And the proxy encryption that we need has to be done on a per message basis. The solution that we have is very low, which requires that on subscribing, the users get a PGP key pair for do the encryption and decryption, and everything else works smoothly. Furthermore, even when group members join or leave the group, no other users are affected. That is, this does not suffer from the one effect end problem. In group communication, the latency requirements are much tighter. You want the all messages delivered in milliseconds. The group membership is still known, but because of latencies, you do the proxy encryption at key distribution. You cannot afford to do it on a per message basis. Now, we don't know the cost because we're still implementing a prototype. We expect the cost to be somewhere between low and medium for the system. By medium cost, I mean that since these are public key messages, the size of